Hello, everyone, and welcome. My name is Rula Deeb. I'm a senior principal at Geosyntec Consultants in California and the coordinator of the webinar series on behalf of SERDP and ESTCP. I have the pleasure of facilitating today's event. This webinar focuses on DoD-funded research efforts to develop treatment approaches for PFAS-impacted groundwater. First, Dr. Charlie Worth from the University of Texas at Austin will present his work on the efficacy of particulate carbon amendments in arresting downgradient plume migration. Charlie's presentation will be followed by a brief Q&A session. Then Dr. Erica McKenzie from Temple University will talk about her research on the treatment of PFAS using regenerable ion exchange resin and activated carbon. Her presentation will be followed also by a brief Q&A session, and we will conclude the webinar with a longer session featuring both of today's speakers. The next several slides provide instructions on optimizing your webinar experience. If you have not done so already, please download Zoom at the link shown here and provide it to you in your webinar registration confirmation email. If you cannot download Zoom, you can view the slides using a compatible internet browser, such as Firefox, IE, or Edge, and by creating a free Zoom account. If you're having difficulties or are unable to view the slides, just try keying in Control and F5 to do a hard refresh of your browser. And if you're accessing the audio through your computer, click the arrow next to the Join Audio button, select Test Speaker and Microphone, and follow the prompts as they appear on your screen. If you continue to have difficulties, just call into the conference line shown here. You may also submit a comment using the chat box. Please use the chat box only for comments related to technical difficulties. The Q&A option should be reserved for questions for the speakers. And in case of continued difficulties, you can download a PDF of the slides from the webinar webpage and call into the conference line provided to you in your registration confirmation email. Another option to view the slides is to go to the SERDP and ESTCP YouTube channel at the link shown here, as we will be streaming live. Today's broadcast is listen only. You may submit questions by using the Q&A box on your screen. You do not need to wait until the Q&A period to submit your questions. In fact, we encourage you to submit them well in advance of the sessions. When you get your questions in, just please, we ask that you add your organization name at the end of that question so that we can identify you during the Q&A session. With that, I'd like to introduce Dr. Andrea Leeson, who's the Deputy Director of SERDP and ESTCP, as well as the Program Manager for the Environmental Restoration Program area. Dr. Leeson has been with SERDP and ESTCP since 2001, and prior to that, she was a research leader at Patel, where she conducted scientific research on in-situ bioremediation and the design and implementation of innovative biological, chemical, and treatment technologies for site remediation and industrial wastewater. Andrea received her doctoral degree in environmental engineering from the Johns Hopkins University. Andrea, please proceed.
Thanks, Rula, and thanks to everyone for joining us today. I hope that you are a regular attendee of our webinars, but in case you aren't, what I would like to do is tell you a little bit about the programs, and then I will turn it back to Rula to introduce our speakers for today. The programs I represent, I'm the Deputy Director for SERDP, the Strategic Environmental Research and Development Program, as well as for ESTCP, the Environmental Security Technology Certification Program. And SERDP is the DoD's science and technology program. You could see this as a traditional R&D program. We've been around since 1991, and we operate in partnership between the DoD, the Department of Energy, and the Environmental Protection Agency. And what we're really looking to do with this program is take fundamental research and use it to impact the real-world environmental management. ESTCP is our demonstration and validation program, and here we take these innovative technologies that have been developed under SERDP or other research programs, and we demonstrate those in the field so that we can accelerate the commercialization or the broader adoption of those new innovative technologies. We're very careful about establishing cost and performance during those demonstrations. We always try to partner with the end users as well as the regulators. And then very importantly is what we're looking to do is transition that technology out of the lab, and then we work to transition it further. We have a number of environmental drivers that guide us with the work that we fund. And first, I'd like to talk about the sustainment of our testing and training ranges, as well as facilities and operations. And as you can imagine, that's a very broad topic. It covers issues such as unexploded ordnance and the munitions constituents associated with them, changing environment, maritime sustainability, and a number of other topics. We are also looking at the reduction of the current and future liability on these testing and training ranges and military installations. And that can include issues associated with pollution prevention to control life cycle costs. And that's really where we're looking at the elimination of chemicals of concern from processes that are used on DoD installations or that are involved somehow in manufacturing, maintenance, and operations. And then we're also looking at impacts from past practices. And those could be impacts from chemicals of concern in our groundwater, soil, sediments. The UXO issue also falls under this topic. And then, of course, we're dealing with emerging chemicals of concern, which the presentations you'll see today are addressing that issue. The focus areas we are looking at within our programs include the PFAS and AFFF, installation restoration, installation resilience, munitions remediation, sustainable energetics, corrosion and repair technologies, as well as electrical infrastructure and planning. And today you'll be hearing about some projects that are working on issues associated with PFAS in the environment. So I put this large flow chart up here just to introduce you to the topic of PFAS as far as what SERDP and ESTCP have been working on. This graphic is also available on our website, and the link for that will pop up in the chat room within the next couple of minutes. And this chart will give you really a synopsis of everything that has been funded on PFAS within SERDP and ESTCP. This is an interactive graphic with a brief description of the topic. And if you click through to the other topics, it will provide you with the number of projects that were funded in that particular year. And from there, there's also a link to a project webpage so that you can get a little bit of information about it. Everything we fund has a project webpage, and then once documents are published, those are also posted on that project webpage. And this all ties into our technology transition efforts. We take this very seriously, that it's very important that the work that we fund gets out into the broader community. And so we do this in a number of different ways, from developing short videos, developing guidances and manuals, in-person training. We have an EnviroWiki that talks about a number of different technologies. And then we hold these webinars as well to give a summary of what's going on with a number of different projects. You can see here a list of upcoming webinars. These are all available now to register. And also, as webinars are completed, the archived versions are also available on our website. And you can go to the website here to both register for future webinars, as well as to view the archived versions. So at this point, let me turn it back to Rula to introduce our first speaker.
Thank you, Andrea. It is my pleasure to introduce our first speaker today, Dr. Charlie Worth, who is a professor and chair in environmental health engineering in the Department of Civil, Architectural and Environmental Engineering at the University of Texas at Austin. Charlie's research focuses on the fundamentals and impacts of pollutant transport and reaction in porous media, with applications to groundwater remediation, geological carbon sequestration, and catalytic water treatment. Charlie is a chief editor of the Journal of Contaminant Hydrology, a licensed professional engineer in the state of Texas, and a board-certified environmental engineer from the American Academy of Environmental Engineers and Scientists. He has a bachelor's degree in mechanical engineering from Texas A&M and master's and doctoral degrees in civil and environmental engineering from Stanford University. Charlie, please get us started.
All right. Thanks, Rula. It's a real pleasure to be here today to talk about our project on the impacts of particulate carbon amendments on the fate of chemicals of concern in groundwater, on behalf of my collaborators and on the students who are working on this. I'm going to start with the technical goals of the overall project and then the objectives of today's talk. We're going to focus on two aspects of our project. We're a little past the first year of it, and so still in the early stages. And we'll look at these efforts and initial results from data mining of field site documents to assess how these particulate carbon amendments are being employed and what these results are. Then we'll look at methods for measuring this particulate carbon amendment breakthrough and distribution. And I'll wrap up with conclusions, benefits to DoD, and then some acknowledgements. So the goal of the overall project is to determine the efficacy of particulate carbon amendments in arresting this downgradient plume migration, and also looking at the operating parameters that maximize this performance of these particulate carbon amendments. And so for today, the specific objectives are to mine published data for trends in particulate carbon amendment remediation performance, and then evaluate these methods to quantify PCA breakthrough in columns. In terms of the overall project, another effort that we're evaluating that is still in the early stages is then looking at these PFAS breakthrough in these PCA amended columns. So first, let's look at this data mining. And so this effort's being led by Chuck Newell and Steve Richardson at GSI. And we're looking at injection practices, volumes of injection, rates, PCA loading, screen lengths, prevalence of barrier versus source type injections, performance measurements like soil sampling, high resolution mass flux measurements, mass balance calculations, and then occurrences of PCA failure and what types of failure occur, such as bypassing or breakthrough. So early in the project then, one of the things we've been developing or starting to develop are looking at what are the upgradient and downgradient concentrations of these perfluorinated chemicals when we have particulate carbon amended treated sites. And so far, as I said, we're in the early stages. We have just 3 data points here. We're comparing these upgradient, that's on the x-axis, to the downgradient concentrations on the y-axis. And if they were the same, if that particulate carbon didn't have any effect, you'd see those dots falling on that dark line that goes right across the center of the plot. They're falling below that, which means we get some concentration reduction. And so far, with the few points we've collected, 2 sites have been in operation for less than 5 years and 1 site for less than 1 year. We see that we're getting about an order of magnitude reduction or maybe a little bit more. And so we'll be continuing to add to this. I just saw in 2022, a paper come out from Grant Carey where he was looking at some of the same metrics. And so we'll be adding those and other studies to this plot. Another thing we're looking at are what are these carbon loadings? And so I've been calling them particulate carbon amendments. Another way we refer to them is a colloidal activated carbon. And so what are these a fraction of colloidal activated carbon that are being loaded into this porous media, into the groundwater? There's been some studies on this. Rick McGregor has a couple papers out, ranges from 0.02 to 0.08%. We're also interested in the lengths of these zones where the carbon's amended. And so from this prior study, 40 to 80 feet, we're also interested in the concentrations that are entering these zones to get a feel on the variability of what type of breakthrough patterns we might have. And so this graphic down below is taken from a paper or a presentation from Grant Carey, and it illustrates nicely some of the parameters we're looking for. So far, looking at 5 different sites, we've seen that this fraction of carbon, this colloidal activated carbon or particulate carbon, varies from 0.0005 all the way up to 0.0027, with an average value of around 0.0014. And so this is very much in the range of what others are seeing. And so we have a pretty good confidence that this is a good representative value. There's certainly going to be higher and lower values. And as we add data to this, we may see that average shift. But just as a point right now, it looks to be close to what others are seeing. Another thing we did with this, just as a kind of point of reference, we took PFAS and looked at isotherms in the literature. And we said, all right, well, what if we have a concentration of 1 microgram per liter? What's the KD value at that concentration? And then from that, with this fraction of activated carbon, we can calculate a retardation factor. And what we get is a value of around 10,000. So at this fraction of colloidal activated carbon in porous media or groundwater, and with PFAS at that concentration, we might expect about 10,000 times slower flow of that PFAS through that particulate carbon amended zone than we have groundwater. So that's a nice result showing or indicating that we're going to get good retardation. We've also been then taking these particulate carbon amendment loadings and looking at, are they changing the hydraulic conductivity? And for this, initially, we're using this Casoni-Kármán equation. We're also going to be measuring this. But for this, with this equation, we look at the initial porosity, the change in porosity when we know the fraction of particulate carbon in the ground, and then we can change based on the initial hydraulic conductivity what that change is. And when we do that, we find for this average PCA loading of around 0.0014, we get a change in the porosity of around 0.0045, and we get a change in the hydraulic conductivity of about 8.3%. So not too large, but there are certainly higher loadings of this particulate carbon amendment reported in the literature. And so some of these changes could become large and perhaps give rise to bypassing. So it's something we want to look for in this literature and report review. Another thing we're looking at then is how do these particulate carbon loadings, how do they affect peak breakthrough? And so there's a couple of approaches we're using. One is mathematical models, trying to simulate this breakthrough, assuming different types of mechanisms. Another is the laboratory experiments that we'll be doing on these particulate carbon amended loaded columns. Right now, we're looking at the mathematical models, and I'll show you some initial results today. There's different types of processes that we could consider that may give rise to behavior that deviates from conventional linear retardation. One of them might be flow path heterogeneity, where we get dilution. Another might be nonlinear sorption, which we often associate with peak tailing. And then another might be mass transfer limited sorption or desorption, where we could have peak tailing and also possibly peak shaving, and I'll talk about that in the next couple slides. So when we think about peak shaving, this comes from a paper from Chuck Newell. We think about, we have our standard breakthrough where we have maybe that breakthrough profile, concentration versus time, or mass discharge versus time that's occurring. And we get kind of this almost symmetrical peak, and it has some peak value. And if we attenuate that, or perhaps if we get nonlinear sorption or mass transfer limited sorption, we might get that mass distributed over a wider or a longer mass transfer length zone, and we get decrease in that maximum peak and possibly below some regulatory threshold value. And so we looked at two models to assess that. One of them was just a simple linear retardation, kind of the standard approach where we have advection, dispersion, and linear sorption. And so here, what we have is, you can imagine we have concentration versus distance here, and it goes from 0 to 2 meters. And in this, you could imagine this to be the zone where we have particulate carbon. And up gradient from this, we could have our PFAS plume, but no particulate carbon. When it hits the 0 meter distance, that's where it encounters the particulate carbon. And we're looking at what happens to that concentration as it moves down gradient over this time period of 800 days. And you can see our velocity and porosity. The time of the pulse is 100 days. We have a dispersion coefficient, 10 to the minus 9 meters squared per second, and that retardation factor is 60. And what you see is that the concentration in the aqueous phase, that's the top plot. We see that as it goes from 50 to 100 to 200 to 400 to 800 days, that concentration decreases over time, but not very much, maybe down to like, I don't know, 80 or 90% of the original value. And if we go to the sorb concentration, the same thing. It's a mirror image, and we just get a little bit of decrease in that concentration. So the next step then was looking at what happens if we have mass transfer limitations. And so now, again, this is that same conceptual model where we have a particulate carbon free zone upgradient, and now we're in this particulate carbon amended zone. And here we have two types of sites. We have equilibrium adsorption sites and then mass transfer limited adsorption sites. And for the mass transfer limited adsorption sites, we adjusted the mass transfer coefficient to demonstrate this effect. And so as the mass is moving through here, some of it's sorbing instantaneously and others slowly sorbing on and off the grains. And what happens, because the mass is slowly sorbing on and off, some of the mass moves a little faster than that would be at linear equilibrium, and some moves slower as it comes off the grains, and it spreads that out. And what happens then is we get this peak shaving. And so this pulse then, the peak concentration is decreased, and that's both in the aqueous and in the sorb phase. And so it's an interesting effect. And what really happens is still, I think, a matter of something to be discovered. We're running or starting to run column experiments. We'll be doing them at different flow rates and looking at this mass transfer coefficient and then quantifying this effect in the future. One more slide on this just to show how the fraction of sites that are equilibrium has a big effect. The two profiles I talked about before were the blue and the red, and now I'm showing it at 200 days. Let's just look at the green one. Here I increase the fraction of sites that are not at equilibrium, the mass transfer ones, to 0.9, so only 10% of them are at equilibrium. And what you see is at 200 days, we decrease that peak even more. You also see an interesting phenomenon when you look at the time where that, or the distance where that peak occurs. It's around 0.3 or 0.4 for the aqueous concentration, but around 0.1 or 0.2 for the sorb concentration. So you see how that lags behind. So now for the second part of the talk. And so here's where we're looking at developing methods to quantify this particulate carbon breakthrough. And our goal is to determine the relationship between these PCA loadings and permeability alteration, and also looking to see how the fluid conditions affect this PCA loading or this particulate carbon amendment loading. We're also starting to do experiments with PFAS breakthrough, but I won't show any of those results today. So we've been using a readily available particulate carbon. It's from US Research Nanomaterials, produced from coconut shells. The diameter is less than 0.5 microns if you look at the box on the lower left. So it has a diameter range there. High surface area, and you can see the particle density and the bulk density. We'll initially perform experiments with this, and we plan to benchmark this against commercial carbons where they're already in a suspension. So the first thing we did with this particulate carbon is look at its stability in solution. And so this just shows a sedimentation test, and this is after 40 hours. And we have 3 different concentrations here, spanning a pretty large range. And so what you see then is after 40 hours, these particles are stable in solution. And so they have good stability. The next thing we did was look at the viscosity. So we have a rheometer, and we measure that viscosity as a function of shear rate. At really low shear rates, the results are not reliable. It's only where the lines settle out at a shear rate of about 10 per second, where it starts to become comparable and reliable for these two different conditions. So here we have water, and we have a particulate carbon loading in the water of 0.001 grams per mil. And we see that that loading has a very similar viscosity to water over that shear range of 10 up to 1,000 per second. One thing to note, we did look at other particulate carbon loadings, and as we go higher, we start to see a higher viscosity. And so we chose this loading because of the similar viscosity to water. The next thing we did was look at breakthrough. And so we have a column here. We have a mixed solution that we're delivering to the column. First, we saturate it with clean water, and then we follow that with the particulate carbon amended water and measure the breakthrough at the outflow. And the flow is from bottom to top. And at the very bottom and the very top in the red boxes, we have filter material. It's a coarser material. And then we have our soil in between. So after the experiment, we can take the column apart and look at the different sections. You can see the filter material on the far right. The bottom is darker than the top, and that's because it has more particulate carbon that's become trapped in it. And if we look from 4 to 3 to 2 to 1, we see it gets progressively lighter. And that's because in the soil, we're having more particulate carbon trapped from bottom to top. So we want to calculate, or we want to measure both the breakthrough, particulate carbon in the breakthrough, but also the particulate carbon in the soil. And that can be a challenge. And so the approach that we've used is we take the soil with the particulate carbon in it. We put it in a tube, and then we sonicate that. And after sonication, the larger soil particles fall out, and left in suspension are these particulate carbon. And then we take the supernatant from that, and we measure it using one of 3 methods. And I'm going to talk about those here in just a minute. I want to mention that we don't have fines in this. There aren't clay particles that would also be suspended, and that would bring about additional complexity that we haven't evaluated yet. One thing, though, that we're looking at is the application for this particulate carbon is in more coarser grained porous media, where you are going to have fewer fines. So the 3 methods, the first method is just turbidity. And so we take either the effluent from the column, or we take that supernatant from that sonicated suspension. We take that, we make dilutions to it, and then we measure the turbidity and calculate that, or measure it based on this NTU units. And what we see is we get a fairly good calibration curve between that particulate carbon concentration and the NTU. The other approach we used was just weights based. And so we take that effluent or that supernatant from the sonicated mixture. We pull it through a filter. Then we put the filter in the oven and dry it. And then we weigh the mass of that. And when we weigh the mass, we compare it to the original mass before we had the carbon trapped in there, and we can measure the mass of carbon. And then the third method is just an image analysis where we have a light box. There's some fluorescent lights at the front of the box. We have a scale at the end of the box, and there we have just a beaker that has our solution in it, and we take an image, and we get a calibration curve that looks like this, where we have our PCA concentration versus the grayscale intensity. So here's the results of our column breakthrough. And first, we're just looking at the particulate carbon amended to the water. We look at the breakthrough on the left plot. We have the relative concentration versus pore volumes. In this case, we're only reaching about 25% of the influent concentration. It plateaus, and then it drops back down. We monitor the pressure during this experiment. And so if you look on the right, the first part in blue, where we have pressure versus time there, is just when we're displacing the air with water. Once we displace that air, then we switch things over, and now we have the particulate carbon amended water, which is being flushed through the column. And we see this gradual pressure increase, and it goes up to about 3 psi. So not a very big increase, from 1.5 to 3 psi in this column system. And we're getting breakthrough, but still accumulation in that column because of the relative concentration being low. So just summarizing, we see that relative concentration plateau and then decrease. The decrease suggests a change in this removal mechanism. Perhaps as we're getting more particles in there, they're starting to stick to each other. And so you're getting that kind of enhanced removal. Because our concentration is relatively low compared to the influent, we're still getting quite a bit of particles accumulating in the column. We've only done this for 18 pore volumes. If we continue doing this, we get more accumulation. And the pressure buildup's relatively minor. And so the next step is, what does this distribution look like along the column length? And so for this, we have the 3 different methods, and this is where the methods come in, and where we're trying to figure out which ones are more appropriate. And so there's a lot of action on this slide, so I'll walk you through it. We have the NTU method on the left, the weight in the middle, and the image analysis on the right. For each method, for example, if I look at the NTU method, I plot the column height on the y-axis versus the fraction of the carbon, or the loading of the carbon, on the x-axis. And then I measure that at in the filter material at the top. And then at each of the 4 sections, because the 4th or the bottom section of soil had such a strong gradation, we measured at both the top and the bottom of that 4th section. and then I measure it at the filter bottom. Down below, I have a mass balance error, and so I have how much mass went in. I know that from the influent, the flow rate. I measure the effluent, so I measure how much mass comes out. And then through these plots at the top, I measure how much mass is in the column. And so the difference between what goes in and out and how much mass gets trapped in there is my mass balance error. And so first, let's look at the top. I'm going to compare the NTU method to the image method. When I look at the results for the filter top and points 1, 2, and 3, they're quite close to each other for those two methods. And so that's quite reassuring. When I go to the top of the fourth section and then the bottom of the fourth section and the filter bottom, the results become very different, where I have the highest particulate carbon loadings. And so that gives rise to very different mass balance errors below. Only 26% mass balance error for the NTU method versus 770% for that image method. But the results are fairly consistent for those top measurements. If I look at the weight method, the mass balance error is small, but when I look at the actual individual measurements, they have a huge uncertainty and they even go negative. I don't have error bars on the NTU or image analysis method, but the Sujin, the graduate student working on this, just presented error bars this morning. She's been working on it, and they're quite small, only about maybe 3 times the symbol size for NTU and image methods, but still larger for this weight method. And so that small mass balance error for the weight method is an artifact. And so the two methods which give the best results are this NTU and the image method. All right. The next thing we want to do is see, we want to start to explore different solution chemistries and see how they affect the method. And so we started with guar gum because it's a common additive as a viscosity enhancer to enhance particle dispersion. We look at different guar gum addition percentages, and we chose the amount that gave very little difference to just the water or just the PCA in water. And so in terms of viscosity, and so that's 0.01%. And so that was our baseline to start with to look at how it affects this method. And so one thing we did first is look at a calibration. And so here's the NTU method versus the image method. And when we have the guar gum in solution, it changes that calibration. And so that guar gum is causing some difference in absorption or reflection of light that requires us to use a different calibration. Right. So the first thing we did then was look at breakthrough. And on the top, I have breakthrough from another experiment with just the PCA in water. It was done for a shorter time period. We get a little higher breakthrough in this case, near 0.4 to 0.5. Again, we see that pressure increase. In this case, we're doing fewer pore volumes, and it only goes from 1.5 to maybe 2 psi. When we compare that to the guar gum, we see we get much more complete breakthrough with the guar gum. It reaches 1 in just a couple pore volumes, and then it starts to drop down again, perhaps again because of that particle-particle collisions. But one thing we do see with this, and which is a big concern with the guar gum, is that we get a big increase in the pressure. And so the pressure is ramping up, and during this time period of 5 pore volumes, it goes to about 23 or 24 psi. And if we were to go above 25 psi, then we start to fluidize and make preferential flow paths through this porous media at a typical groundwater depth. So just summarizing those results, this relative concentration breakthrough with the guar gum is higher. And so we have less particulate carbon retained in the column over multiple pore volumes. With the guar gum, it's concentrated, and we'll see this at the column inlet. So we get much more being filtered right at that column inlet between the filter material and the soil. And perhaps it's due to this small or large to small particle transition. And then as it moves through the column, we get less deposition overall. And then we get this very large and worrisome pressure drop with the guar gum. So that becomes quite large over just a few pore volumes. When we look at the depth profiles, again, we get very similar results with the NTU and image method. We're having still problems at the bottom. And in the newest results that Sujin shared with me, she thinks she figured out the bottom issue. We have to use a high shear when we're separating out or suspending the particles in order to get a reproducible or a good measurement. And so I think that error is going to come down now. We're going to get much better mass balance errors and agreement at those highest concentrations for the NTU and the imaging method. The weight method, the values are still a little lower. Also, not shown here, but in the newest results, we have the error bars are still quite a bit larger for the weight measurement than the NTU or the image analysis method. And the reason is that filter weighs quite a bit, and the carbon you trap in it is only a very small weight. And so we're subtracting two large numbers from each other, and that just gives rise to error. So kind of overall, it looks like both the NTU and the image method will be suitable, and we're going to confirm that in the coming month or two. But they're both looking very promising. And most of the error that we have for those methods is just being careful with volume transfers and making sure things are very well mixed in those processes. So conclusions overall, data mining results, that particulate carbon reduces downgradient PFAS concentrations. At average PCA loadings that we find, the hydraulic conductivity decreases by about 8%. This particulate carbon potentially impacts peak breakthrough concentrations, and that's something we'll continue to explore and looking at the effects of possibly mass transfer or nonlinear sorption. In terms of the PCA breakthrough, both this NTU and the image analysis best quantify both the effluent and also these concentrations along the column length. The Gorgums improves the breakthrough overall, but with an unacceptable pressure increase in our experiments. So in terms of benefits to the DoD, we're providing tools to evaluate the effects of this PCA loadings on porosity, hydraulic conductivity, and peak shaving, and also collecting data to support that. We're providing methods for others to use to assess these PCA concentrations in column effluent and along the soil column, and looking at how possibly different fluid combinations affect that. And looking at how Gorgum affects this PCA breakthrough and the quantification and how we can account for that. Acknowledgements, my collaborators are a geotechnical engineer, Chadi Al-Motar, here at the University of Texas, Austin. I already mentioned Chuck Newell and Steve Richardson at GSI, who've been leading the data mining effort, along with Hassan Javad, another employee, and then Tom Holson for the PFAS analysis work that'll be coming. And then the students here, Dana Klein, Sujin Park, Michaela Rigg, and Ziji Zhang. And I think that's all. Thank you.
Thank you so much, Charlie, for a very engaging presentation. As a reminder for everyone, please submit your questions using the Q&A box on your screen. We have received a number of questions for you, Charlie, so we'll go ahead and get started. This first question is from the California Regional Water Quality Control Board and the Central Coast region. For what lithology types would this technology be applicable?
Yeah, I think we're looking at injection into porous media. And in order to inject through porous media, it has to have a fairly good hydraulic conductivity. And so we're looking at ideally, fine to coarse sands, but probably also silty sands we could inject into. You can apply particulate carbon amendments within clays, fine material, but there you're looking at a fracturing technique where you're injecting at a higher pressure and creating these fractures where you're depositing those carbons.
Thank you so much, Charlie. This next question is from the North Carolina Department of Environmental Quality. Adsorption has been modeled as a reversible process, which makes sense for the anionic nature of many PFAS. Is there any evidence that aging or longer contact time could lead to some irreversible sorption from the integration of PFAS into the colloidal organic material?
Yeah. There's been a number of studies, not with PFAS that I'm familiar with, but with kind of your more hydrophobic adsorbents and adsorbates, such as PAHs, chlorinated solvents, and looking at, I guess, hysteresis or some irreversible bound fraction. Oftentimes, within the time frame of experiments, when people look at adsorption and desorption, they find that there's a fraction that doesn't desorb. Generally, it's a small fraction, and it's not clear with very, very long time if that would eventually desorb, if it's truly irreversible, or if it's just bound perhaps more tightly, or if the concentration gradient is so low that it's just a very small driving force for removal. But I would say that there's certainly this fraction that tends to stay behind for all organics and comes off very slowly. And so I think there is going to be this effect, at least whether it's mass transfer or true sorption hysteresis, that is giving rise to this fraction that sticks behind and very, very slowly comes off. Whether it never comes off, I don't know. But yeah, thanks.
Thank you so much, Charlie. This next question is from the University of Arizona. Can you explain the experimental method for measuring the change in porosity with PCA loading?
Yes. In this case, we're measuring just the fraction of this colloidal activated carbon within the column segment, and then we use the particle density to calculate a volume. And with that volume, then we just subtract it from the original pore volume to get that change in the porosity. So we don't measure the change in porosity directly. That change in porosity is quite low. And so we're looking at, maybe something on the order of a few percent change. And so that would be very difficult to measure with a tracer study. I don't think you could do it. I don't get the method is sensitive enough.
Thank you, Charlie. This next question is from Regenesis. In your modeling efforts, how are you evaluating competitive sorption in mixed plumes where contaminants other than PFAS are present? Yeah,
that's a great question. There are different approaches to model competitive sorption. I would say the one that has shown the most promise in my own experience over the years has been the ideal adsorbed solution theory, where if you have the individual sorbate isotherms, you can estimate what those competitive isotherms will look like, and then you can use that in the model to simulate that competition as you're having breakthrough occur. There are others. There's, I think, a competitive Langmuir. There's the Polanyi theory, so those are possibilities. But that ideal adsorbed solution theory is given the most promise in my own experience. That requires measuring the individual sorbate isotherms, or at least the major ones, and then coming up with some way to estimate the minor ones. And so how we account for many, many dozens of compounds yet, I haven't thought, or I don't think I have a good approach for that yet. I've just been thinking about it, but we'll have to come up with being able to measure a few, and then based on properties of the chemical, I think, estimate the individual isotherms for many others.
Thank you, Charlie. This next question is from the California Regional Water Quality Control Board in Santa Ana. The injection method from bottom to top in the column study is different from what is typically done in a field application of PCA. Can you comment on what the expected differences might be between your lab study results and the distribution of PCA in a soil matrix following PCA injections?
Sure, yeah. The particle size we use is less than 0.5 microns. And we've shown over 40 hours that it stays suspended in solution. And so I think gravity effects from that would be very small. And so I think in terms of the particles themselves, injecting them upwards or injecting them horizontally won't make much difference because of those very small gravity effects. If you get larger particles, it would certainly make a difference, carbon particles. I think one advantage of the upflow in the lab experiments is a uniform flow distribution of the water, a little less likelihood of preferential flow just because of the gravity effect on the water. I think you're perhaps a little more preferential flow on the horizontal. And so that might be the main difference.
Thank you. This next question is from the University of Cincinnati. Does the guar gum cause aggregation or clumping of the PCA particles, or do you observe the opposite?
Yeah, that's a great question. Sujin is getting trained now, or setting up a time to get trained on the kind of particle size analyzer. And we suspect that with the Gorgum, there's some bridging between particles and that we're getting a little bit larger kind of, mean or average particle size. And that could be why we have so much accumulation between that coarse filter material and the soil above it. But that's something we still have to confirm. And so I think what you're suggesting is probably correct, but we haven't measured it yet.
Thank you. This next question is from Cascade Environmental. Have you considered anchoring technologies with the carbon to minimize breakthrough?
Oh, could you repeat the question, please?
Yes. Have you considered anchoring technologies with the carbon to minimize breakthrough?
Anchoring technologies? I don't know what that means.
Mobilizing them in place is how I'm reading this.
Oh,
mobilizing the carbon on something.
So maybe affixing the carbon to another carrier or another particle. Is that what okay. I guess directly attaching it to another particle, we haven't considered that. I'll have to think about that. Certainly when we have Gorgum or other type of polymeric additions, we're going to get coating of those particles with the polymer, which isn't anchoring it, but it is a way of modifying the particle itself in terms of the surface charge to perhaps increase its distribution or improve its distribution in the groundwater. So those are good thoughts, and I'll have to think more about anchoring it to another particle. I don't have a good answer for that one.
All right. Well, thank you, Charlie. We still have a lot of questions, so we'll try and get back to you towards the end as time permits. But again, thank you for a great presentation. We're going to go ahead and transition to our last technical presentation of the day, which will be given by Dr. Erica McKenzie. Erica is an associate professor in the Department of Civil and Environmental Engineering at Temple University. She has been working on PFAS-related topics since 2013. She currently leads an NSF-funded project on PFAS interactions with organic matter and the impacts on transport. She's also heavily involved in a lot of other PFAS projects on partitioning from biosolids and approaches to immobilizing PFAS in biosolids. Beyond PFAS, her research group evaluates a range of chemical contaminants, including nutrients, metals, solids, PAHs in stormwater runoff, considering a range of media, including incoming water, pore water, local groundwater, soils, plants, and potential sorbent amendments. Erica has an undergraduate degree in environmental engineering from Colorado State University and a doctoral degree in civil and environmental engineering from the University of California, Davis. Erica, please go ahead and get us started.
Thank you very much to the organizers for giving me this opportunity to highlight our work. So to give you a preview of what I'm going to be talking about today, I'm going to cover our 3-year project, which is essentially complete. We are in the report and paper writing phase. And so you're going to get a summary of the different components of our project. This includes doing batch equilibrium removal and regeneration studies, then using those to inform our pilot scale removal and regeneration efforts, and then also our sonochemical treatment of the regenerant to degrade the PFAS. I will close out with some conclusions and discuss how this project is a benefit to the DoD. So we had some background on PFAS from our last presentation, but I'm going to highlight a couple additional points. So these are per and polyfluoroalkyl substances, and all of us, both in the technical field and in general audiences, are learning more about these compounds each day because they're gaining a lot of attention. And some of the reasons that they're gaining that attention is that some of these compounds are persistent, bioaccumulative, and toxic. And we're also recognizing now that there are lots of different sources, lots of different matrices that they occur in, and thousands of compounds. So this is a very broad problem that we're trying to face. With respect to the DoD, A lot of the emphasis has come through PFAS historically being included in aqueous film forming foams, and that has led to contamination at many, many DoD sites. And because these compounds are persistent and also some of them are comparatively more mobile, it creates some treatment challenges. For our project, we are trying to explore some of those treatment approaches, looking at using media to remove the PFAS in a pump and treat style of setting, and then using sonochemical degradation approaches. Here's a highlight of what we have done. So we focus primarily on 14 PFAS, and that includes 8 PFCAs, 4 PFSAs, and 2 FTS compounds. We use those to evaluate the performance of 5 anion exchange resins and 1 activated carbon, which we included as a reference. And then we included 1 degradation technology, so that's our sonochemical treatment. As I mentioned previously, we started out with laboratory batch tests, and then we moved on to a pilot scale test, and you'll hear about both of those today. Overall, our goals are to look at the strengths and the limitations of these treatments to understand their potential application. In our batch removal, we started out with doing equilibrium tests, and these are isotherm tests to try to understand the concentration effect. This was using an artificial groundwater that contained some background electrolytes and buffering, and we had an initial concentration of our PFAS that was approximately 4 micrograms per liter. We mixed these end over end for 7 days because we were intending to achieve equilibrium. And what you can see are some examples on the right. We can see that we tested out 7 different initial seven different masses, and that had allowed us to look at the concentration effect. And as these examples show, we generally saw that the isotherms were linear, and that was relevant for these environmentally relevant concentrations that we saw. So as you can see on the x-axis, our equilibrated concentrations are in the nanogram per liter range, and so things that you would find at a contaminated site. Now, the nice thing about doing these isotherm studies, and particularly that they ended up being linear, was it allows us to summarize the absorption capacity into a single value. So that's going to be our K linear value. And so now we can look at the performance across the different compounds that we were considering and across the different media that we were assessing. So on the graph on the right-hand side, you can see that I have the compounds arranged. So I have the PFCAs on the left, PFSAs in the middle, and then FTS compounds on the right. And for each of these different groups, I have them arranged by increasing chain length. And again, on my y-axis, I'm plotting that linear isotherm result, so K sub L. And what we can see is this allows us to compare the performance of our different media, shown in the different colored bars. So as general trends that we can observe is that generally the removal or the absorption capacity increased as we had an increasing chain length. So that's what you can see here in these trends. We also observed that generally we had greater removal for the PFSAs compared to the other compounds when you look at equivalent chain lengths, and that the FTS compounds had less removal, lower K sub L values for an equivalent chain length. Since our project was specifically focusing on evaluating the media performance in a comparative way, we took this same data set, so these K sub L values, and we compared each of our media to the performance of the activated carbon reference material. And so this is the ratio of the resin K sub L to the activated carbon K sub L. And I should have pointed out on the last slide, the y-axis was log distributed. And so this is also a log y-axis. So we see that values that are above 1 indicate that the resin outperformed the activated carbon. And in cases when we have values below 1, that indicates that the resins were performing less well, had a lower K sub L value than the activated carbon. And as we can see in these trends, the resins commonly had better performance than the activated carbon for some of our shorter chain length compounds shown over on the left. And as we increased the chain length, the activated carbon ended up having a greater K sub L value, a higher absorption capacity. We can also see that there are trends among our resins that we tested. And so the blue line, which is PFA-694E, had the strongest, the highest absorption capacity. And that was expected. It was included in this study as a resin that was anticipated to have very strong performance. So from this, it allowed us to identify our top performers, and that allowed us to proceed forward with a subset of these media. Our next step was to try to look at the potential regeneration for some of these select resins. So here we're investigating 3 of our ion exchange resins. We're again doing this in a manner that is intended to evaluate equilibrium performance. So we're using 7 days of mixing. And we start by loading those with PFAS with the same approaches that we used for the isotherms. And then we used regenerate solutions applied for 7 days to see how much we could pull off of the resins. So here's an example of the data that we get out of this. We tested 12 regenerate solutions. And this is the results for PFOA presented as the percent that was regenerated. So higher values indicate better regeneration. On the left-hand side, these are our aqueous regenerate solutions. So it's water with salt added. And the salt was added at 1% sodium chloride or an equimolar concentration for the other salts. And you can see here for PFOA that we did have some regeneration with our aqueous brine solutions. And if I were showing the data for shorter chain length PFCAs, we would see that that regeneration effect was even stronger. So for our short chain length PFCAs, we had pretty good regeneration. Now, as we look at PFOA here, we can see that when we include methanol, and that's shown on the right, we tested both a 50% and a 70% solution, but that substantially increased the amount of PFOA that we could regenerate. And that was also true for our longer chain length PFCAs. So the addition of that organic solvent improved the performance. When we look at our PFSAs, and here on the right, I'm showing PFAS as an example, we saw that our aqueous brines were not effective for regenerating those. So again, if we're looking on the left-hand side, all of these are very low values, indicating that the regeneration was low. But when we include the methanol at either 50 or 70%, we saw that the regeneration increased substantially, and so that we had nearly complete regeneration. Again, we did test out a number of different salts, and we saw generally that chlorides work better than hydroxides, and that for our cations, sodium and ammonium typically had about equivalent effects. So this allowed us to identify the salts and the solution composition that we wanted to use going forward. We did also want to test and confirm that it wasn't just a single use or a single regeneration. So we wanted to test multiple cycles. So here we're showing 3 repeat cycles of applying PFAS and then regenerating them, applying PFAS, regenerating them, applying PFAS, regenerating. And I'm showing it for 6 of our compounds. These are with a methanolic regenerant solution. So it's 50 or 70% methanol with 1% sodium chloride. And what we can see is that the regeneration effectiveness is similar for each of the regeneration cycles. There's no trend one way or another. And for most of our compounds, we're seeing complete regeneration. So that indicates to us that the regeneration is both effective and can be done over repeat cycles. So summarizing some of our multi-cycle findings, when we used aqueous brines over multiple cycles, and I didn't show this data, but there was a modest decrease in the short chain PFCA removal. And so that indicates that some of that absorption capacity is lost over time. However, when you include either 50% or 70% methanol, then there isn't any loss in performance, and that we do see consistent results across the range of PFAS that we tested, so those 14 compounds, and consistent results among the 3 resins that we evaluated. So it seems that it's a promising approach to be able to regenerate these resins for repeated use and PFAS removal. Next, we used a pilot scale approach to try to test and confirm our batch results. For our pilot scale test, we had 3 resins that we used. So the first one is PFAS-694E, and that was our strongest performer from our initial batch testing. We included A592E, and that is one of the regenerable resins that we tested, and it's a strong base resin. And then we used USA 21107. That's also a regenerable resin that we tested and is a weak base resin. As we had previously, we included the Calgon F400 as our GAC reference, and we installed these into a drinking water treatment plant as a side stream treatment. And this is for a location in southeastern Pennsylvania. The pilot scale system was deployed for 6 months. And to give you an idea of some of the water quality, or at least the PFAS contamination at this site, we had around 500 nanograms per liter of PFAS. We had around 230 nanograms per liter of PFHXS and 200 nanograms per liter of PFOA and about 110 nanograms per liter of 6,2-FTS. So we were analyzing 24 compounds for this aspect, and these were the 4 most common PFAS present in the contaminated groundwater. So it was a 6-month test, and this was done as 2 months worth of applying groundwater, and then the regenerable resins would be taken offsite, and they would be regenerated every 8 weeks. So there were 3 regeneration cycles total. So to give you an idea of the approach a little bit more, our project was intending to test out relevant treatment approaches. And so it meant that when we were looking at the empty bed contact times, we wanted to reflect the fact that GAC typically has a longer empty bed contact time. So here we're using 10 minutes, and that's representative of a typical setup. For our 2 regenerable resins, those were operated with a 3.7 minute empty bed contact time. And again, that is typical or in the range of typical for anion exchange resins. With PFAS-694E, we used a shorter empty bed contact time, and that was to ensure that we saw some breakthrough. So it was an accelerated process. Now, on the right-hand side, I'm just showing you one set of data that allows us to compare the performance. So this is PFOA. And here, because we're operating them at different empty bed contact times, it means that our data is not going to be equally spaced. So we're going to end up having many more bed volumes treated with our 694E, and that's the yellow line that's down at the bottom. And so we see that here, this is just the start of the test, but we're seeing that 694E was achieving really strong removal. So that is what we would have expected based on our batch results. And so it is outperforming the other media. Among our other media, so looking at the 2 other anion exchange resins and our activated carbon, generally they were showing fairly similar performance, but again, they have slightly different empty bed contact times. Now, I'm going to start with highlighting the FTS and the PFSAs, and then we'll move on to the PFCAs. With the FTS compounds, and that's what I'm showing on the right, we do see that you have the shorter compounds break through earlier. So 4,2-FTS, which is our shortest compound shown at the top, you can see that you have fairly quick breakthrough. The black line represents the influent concentration, and then each of the media is shown in one of the colors. And so you can see that you start having an overlap fairly quickly with the influent concentration. As you move to the middle, which is 6,2-FTS, and the bottom, which is 8,2-FTS, you can see that it takes more time for breakthrough to occur. For our PFSAs, which I'm not going to show at all, those were very well removed, and in many cases, we had non-detectable concentrations in the treated effluent water. For PFCAs, you can really start to see some of these trends. So here, this is our PFCAs and showing breakthrough, where the shortest compounds are breaking through earliest, so PFBA in orange. And you can see this chromatographic separation where the longer compounds, which have a higher absorption capacity, are better retained on the column and so take longer to break through. We don't see evidence of PFAS release. In some previous work by others, they have seen that elevated concentrations of PFAS, as the longer chain length compounds come in, they kick off the shorter chain length compounds, and that can lead to values that exceed 1 or in a C over C naught presentation. And we don't really see that in our experiment. So it seems like they're being retained within the column. This here is an example for 694E, but we saw the same general trends for our other media as well. Now, so far I've talked to you about the 14 compounds that we tested in our batch systems, and then highlighted the ones that we saw present in the field system. We acknowledge that this is just a subset of the PFAS that are present. And so we also wanted to do some limited inquiry to try to figure out how our media was performing for these other PFAS that are available. In order to do this, we use the total oxidizable precursor assay, TOP assay. And this is an approach that employs a chemical oxidant at elevated pH and temperature to convert many precursors, which we can't necessarily measure, into a form that we can. And what this told us is if we look at the contaminated groundwater, our total targeted PFAS were around 800 to 1,000 nanograms per liter. So those are the results that I've already shown. When we look at the precursors that are revealed through this TOP assay, it means that there are around 500 nanograms per liter additional precursors present in our system. When we look at the water that's treated with our anion exchange resins or with our activated carbon, and that's shown on the right, we see fairly rapid breakthrough for these precursor compounds. We don't know specifically what compounds they are, but our TOP assay indicates that we're seeing pretty rapid breakthrough. One thing to point out, again, we have different empty bed contact times, meaning we're treating different bed volumes for each of our different resins. And so PFA-694E, which is our strongest performer for the anionic PFAS, that's presented on the top axis. And so it has 10 times the bed volumes of something like activated carbon, but it also has very rapid breakthrough of our precursors. By contrast, the Calgon F400, which is shown here in purple, that we see some breakthrough, but it's still able to remove a moderate amount of the precursor PFAS throughout. And so it highlights to us that those hydrophobic interactions are important for those broader classes of PFAS. Just to summarize some of these findings from our pilot scale system, we can look at this breakthrough both in a qualitative sense, like I previously presented, but we're also working now on modeling some of these results so that we can be more quantitative about it. When we look at the trends among it, A694E was the strongest performer, and that's especially noteworthy since it had a short empty bed contact time. The other media had similar performance, but the F400 GAC did outperform for removal of the precursors. When you're selecting it, you also want to think about some site constraints, and we'll get into those a little bit further, but those can include size, the PFAS profile that you're trying to treat, and your ability to regenerate things on site. For PFAS considerations, we want to recognize that the short chain PFCAs and the FTS compounds are going to break through faster. And so that may drive when you need to regenerate or replace your resin. The removal, having that in mind and recognizing that PFOA is often one of the higher concentration PFAS, that is often going to be the primary driver that indicates when regeneration or replacement is needed. Lastly, site water quality considerations should be included in the evaluation. So that includes PFAS concentrations, but also consideration of other water quality parameters that may require pre-treatment prior to using an ion exchange, or it might require, or it might change the absorption capacity. We used regeneration for the field site, and here we're using 70% methanol with 1% sodium chloride. And we see that that is effective at regenerating the resins. So we see that that can be done in a fairly small number of bed volumes applied, and that it does completely regenerate the performance. So the top graph shows us that that regeneration was achieved, and the bottom graph shows PFOA breakthrough from our columns in 3 subsequent regeneration and reuse cycles. So that makes us feel very confident about this approach. Last component of my presentation will focus on the PFAS sonochemical destruction. So this was sonochemical treatment operated at 1,000 kilohertz. And you can see that it's operated over an extended time. So these were tests that were conducted for 16 hours. And we can see that we achieve good treatment for both still bottoms, which are presented on the top, so elevated salts present, and then also for still bottoms with the presence of 5% residual methanol. The presence of methanol did slow the treatment, but it didn't prevent the treatment from occurring. We also see that the treatment is faster, the degradation is faster for our longer chain length compounds compared to our shorter chain length compounds. We were able, those previous results were for synthetically created still bottoms. These are still bottoms that were provided from a treatment site, and so confirming that it works with real material. And these still bottoms had very elevated total organic carbon present in them, and so it required additional treatment time. You can see that these tests are out to 64 hours, but that ultimately it was capable of achieving destruction for these PFAS compounds. The PFAS destruction was improved when an elevated pH was used, and that's likely associated with increased creation of hydroxyl radicals. So some conclusions from this presentation. First of all, the absorptive media are effective for removing PFAS compounds, and the anion exchange resins are particularly effective for those anionic PFAS. However, there is going to be some absorption capacity limitations, and so operators need to be mindful that there's going to be compound specific considerations for breakthrough, and particularly those short chain length compounds are going to be the ones to break through faster. When you're thinking about selecting a media, there are a number of considerations to evaluate, and that of course includes the range of PFAS that are present in your water, including short chain and or precursors, as well as thinking about your site-specific factors on the amount of space that you have, the flow rates that you would need related to those empty bed contact time questions, and then also would you be able to regenerate on site? We are working right now on a technology treatment selection tool, and the goal here is that it will consider, and it should consider, the cost associated with degradation and disposal. So this project highlights a couple benefits to the Department of Defense. And it's first that we need to consider the whole system, meaning that if you have a large dilute plume of PFAS potentially, you should consider a technology that allows you to remove and concentrate those PFAS, for example, in an ion exchange media. And so activated carbon and anion exchange can both be used for that purpose. The ion exchange resins are often going to be better for those short chain length PFAS compounds, and GAC better for the precursors. We also need to consider how destruction can be achieved. And so the sonochemical treatment is an approach that was capable of degrading the PFAS, both in still bottoms and when there was a bit of methanol present, and it largely fully mineralizes them. Lastly, a treatment train is a potential approach that should be explored. And this might include a regenerable resin coupled with a single-use resin, and then with a sonochemical degradation option for the regenerate solution. And as I mentioned, we are working on a resin selection tool. So with that, I want to acknowledge my contributors. So Aptim was the lead organization on that, and that was led by Mark Fuller, and Paul Hatzinger also contributed. Purolite, led by Francis Boudou, are our experts for the ion exchange resins. And then at Temple University, it was myself and Raminder Suri. And I don't have them listed on the slide, but I do want to give a big shout out to the students that worked on this. So Yi Zhang was a postdoc that worked on this project, and Yassine Al-Kharikouli was a grad student that has been working on this project. Thank you very much for your time.
Thank you so much, Erica. We've received a number of questions. The first one is from the University of Cincinnati. Beyond performance, what are other considerations in selecting regenerants? For example, what are the sustainability considerations, if any, for the use of methanol as a regenerant solution?
That's an important consideration. When you start using regenerants, and I'm saying either aqueous brines or ones with methanol, cost is going to be one of the considerations to include. And so that's the cost of the salts, and then notably the cost of the methanol or a different organic solvent. Of course, another aspect that needs to be considered is the safety. When you start using an organic solvent, it raises additional safety concerns and requirements because methanol or another organic solvent has elevated risk with it, both in terms of exposure and flammability. So that's another consideration that needs to be included. Lastly, and that can relate to whether or not you're able to regenerate on site or whether it needs to be moved off site for regeneration.
Thank you, Erica. And this is a very related question from the U.S. Army Corps of Engineers. You talked about worker safety handling methanol, but are there any human health impacts if the ion exchange resin is used for potable water applications?
Thank you very much for raising that point. So when I have talked about this with our collaborators from Purolite, they have indicated to me that usually organic solvents are not used with drinking water applications. So I am sharing that from my understanding, but I would be happy to follow up and put this question asker in touch with Purolite, who they can provide a more thorough answer.
Thank you so much, Erica. I will share with you the author of that question, and you can follow up with them offline. This next question is also from the University of Cincinnati. In the sonochemical process, if there's a lot of TOC background concentrations, it could interfere and make the process more expensive. So have you considered a treatment approach to remove, or any approach to remove the TOC before the sonochemical process to reduce costs and improve efficiency?
You point out a very good aspect of that. So, you know, as the slides show, it really did increase the treatment time, and so therefore would increase the treatment cost. We have talked about some approaches that could be potentially applied to address that TOC in advance, but we haven't experimentally worked on them at all. So I think it's an important point that's been raised, but I don't have any experimental results to inform that discussion.
Thank you so much, Erica. This next question is from Johns Hopkins University. Did you try to analyze and identify the destruction byproducts?
So the short answer is yes, but I will definitely want to connect you to Mark Fuller to get a fuller answer on that. We did see some formation of some volatile organic fluorine products. So that was one aspect. And so they did some GCMS work to look at that. There was some creation of some shorter chain length compounds. So you saw how there was an original increase and then decrease. And so there has been some efforts on that front to try to understand. And I should also highlight that the degradation products did seem to shift based on what pH was used during the sonochemical treatment.
Thank you so much. This next question is from the Arizona Department of Environmental Quality. Can brine generated from reverse osmosis be used again as a regenerative agent based on your experience?
Interesting question. So I'm going to speculate here for a second. I would think that the elevated salts that would be present in the RO retentate would be useful. I would worry that there would be other things in the retentate that might cause problems. So if you had elevated TOC, dissolved organic carbon, that could be a problem. So for example, when you're using ion exchange resins, one of the water quality parameters that needs to be considered is the dissolved organic carbon concentration. And if there is elevated dissolved organic carbon in the feed water, and I'm just talking about the treatment side, not the regeneration side right now, but if there's elevated dissolved organic carbon in the water, then that can cause issues. And so it requires pre-treatment. And I would think that the same considerations would apply for selecting a regenerant solution.
Thank you. This next question is from the House of Representatives. Given the new proposed EPA regulations and the low levels that are expected to move forward, what would you recommend given the results of your work when we're talking about removing longer chain versus shorter chain compounds? Which could you, based on your own work, speculate whether GAC would be the best available technology, or ion exchange, or a combination of both? Or such decisions have to be made on a site-specific basis?
So first, I might have misheard this, but I want to clarify that I'm not proposing any regulations. This is just looking at treatment to try to achieve treatment goals. But to get to the question asker's last point, there isn't going to be a single answer that is going to work for, that is likely to be the best option for every system. There's a lot of different considerations that go into selecting the right tool. So the question asker was highlighting long chain versus short chain. As we saw, the ion exchange resins often outperformed the activated carbon for the short chain removal. So if you have a system, a source water that has a lot of short chain compounds in it, you might think that the ion exchange resins are a better option. If you have a system that has a lot of precursors in it, then it might be that the activated carbon is the better option. There are different requirements that are needed, again, for that pre-treatment consideration for ion exchange resins. So that might also be one of the things that's considered in selecting the right sorption media. So it's going to be a multifaceted consideration. And that's one of the things that our collaborators at Purolite are really trying to take into consideration as they're developing that media selection tool, and to really guide that process and make it more straightforward.
Great, thank you so much, Erica. We're just going to take a few questions for Charlie, and then we'll get back to you because a lot of questions are still coming through. So Charlie, if you don't mind coming back on the line, this next question for you is from the US Navy. How is the carbon particulate matter collected after being injected in the subsurface? Or do you have an estimate for how long the PCA can remain in groundwater? So can you just, based on your lab work, share some observations?
Yeah, in our own lab work, right, we take apart the soil columns and then take the soil with the PCA in it and then sonicate it. And then the colloidal particles, the carbon stays suspended, and we take that supernatant and analyze it. In the groundwater, I believe people are taking cores, and in those cores, and depending on the PCA loading, I'm not exactly sure the methods, the different methods that have been used. One approach would be just mass, and if the amount of organic carbon in the groundwater sediments is low relative to the particulate carbon that's in there, then you could just weigh a before and after, like a 550 combustion, I think, and get the mass difference. That might be one approach. You could also sonicate and suspend it and then do that, but I'm not sure if anyone's done that as of yet. In terms of how long it stays in there, the particulate carbon becomes immobilize. It sticks to the soil grains, become wedged into little grain connections. And I believe it'll be in there for a very, very long time. It's a relatively kind of inert material in terms of being degraded itself. So I would expect that would be there a very long time, but it will become exhausted over time with respect to its sorption capacity. And so that would depend on the concentration of the pollutants and natural organic matter, and that groundwater flow rate in terms of the mass flux coming through that activated carbon zone.
And a very related question, Charlie, from the US EPA. Do you expect the particulate carbon that gets immobilized in the porous media to degrade with time?
Yeah, I would not expect the particulate carbon to degrade over time, at least the time scale of our lives. This activated carbon is, it's highly condensed aromatic groups that's relatively inert to biological and chemical breakdown. And so I would expect it to be there for a long time, not necessarily active, but certainly there.
Great, thank you so much. Perhaps one more or two more questions for Erica before we wrap up. Thank you, Charlie. You observed that linear isotherms fits were generally appropriate for that, for your data. Did you expect that, or were you surprised by the great fit?
Thanks. I would say that we weren't surprised, but I do want to highlight that this is a different finding than what some other people have seen. So our goals in our project were to conduct these isotherms at those low concentrations that are environmentally relevant. And what that means is that the PFAS are only occupying a really small fraction of the ion exchange sites that are available on the resin, something like maybe 1% of the sites. And so it means that we're not limited in our supply of ion exchange sites that are present. And additionally, from other people's work, we know that there are other mechanisms, so some hydrophobic mechanisms that can contribute to removal. So at those low concentrations, I think it's understandable that you would have a linear isotherm. Now, if you start going into higher concentrations, many other people's work will demonstrate that it deviates from a linear fit. And that's as you start filling up more of those sites.
Great. And another question for you from the Central Valley Regional Water Quality Control Board in California. The influent concentrations you tested seem to be at the part per billion level. Will the conclusions of your work be applicable to groundwater when we're looking at TPT levels?
The concentrations that we were seeing in the pilot scale testing site were generally in the nanogram per liter range, so the part per trillion range. It is a site that has known PFAS contamination, so it's going to be higher than a location that doesn't have any specific sources, but the concentrations of PFAS, I'm saying this from memory, but were between 200 and 300 nanograms per liter. So still in that part per trillion kind of concentration.
Thank you for the clarification. What about some of the supporting laboratory work that you've done? Would you expect?
Yeah.
Great.
Yeah, sorry, thank you.
All right.
Let me just, okay.
Go ahead, Erica.
Okay, sorry about that. These concentrations that we were spiking into our systems were starting at around 4 micrograms per liter, but the equilibrated concentrations ended up being in those hundreds of nanograms per liter. So the concept there, or the approach there, was intended to achieve environmentally relevant concentrations. We do see a lot of agreement between our batch results, the trends that we saw in our batch results, and those that we saw in the field sites or the field system. So that suggests that, again, we're achieving that environmentally relevant both concentrations and also the mechanisms. There were a couple cases where we did see some notable differences between our lab studies and what we saw in the field. And unfortunately, we ran out of time to further investigate those, but those are places where there might be some deviations. And nicely, since we have both the lab data and the field data, we're aware of those differences. And so, can share that, and that can allow us to probe further in the future to better understand.
Thank you. That was a really important clarification. We're going to go ahead and wrap up. I just want to remind you that our next webinar is on April 20th in 2 weeks. It will focus on DoD-funded research efforts to evaluate the performance of PFAS-free firefighting formulations and the Navy's efforts to develop a fluorine-free foam military specification. This webinar will feature 2 speakers, Mr. Jerry Beck from Jensen Hughes and Mr. Tom Raffini from the Naval Sea Systems Command. Registration is open, so please visit the SERDP and ESTCP webinar webpage to register for this and other webinars to the beginning of 2024. Before we conclude, I'd like to remind you, as Andrea said, that both the audio and a copy of the presentation of today's session will be archived on our webinar webpage in case you'd like to refer to them in the future. Thank you again to our speakers, and for our audience members, if you could please take a moment to complete the survey that will pop up on your screen, we would truly appreciate it. This concludes today's webcast. Thank you so much for joining us.